Good morning, good evening, good afternoon, depending on where you are. Today is May 8th, and this is another of our batch working group um, meetings. My name is Mate, and I'll be your host today. I'm joined by Kevin and Swati, and we have a pretty packed agenda, so let's get into it. Kevin, you have the first topic.
Mostly, I'd be quick. Basically, we had to cancel the Pacific Coast time because we don't really have a host that can reliably make that time, and there was less demand. So I was going to propose that we make this meeting time biweekly going forward until I'd like to have us meet twice a week or biweekly. Uh, there's no objections. Or if there's objections, let me know. But I feel like this is probably a good idea. All right. That's all for me. I'll set up a calendar invite then.
Okay, sounds good to me. Having not hearing any objections, I believe we can just proceed with the change. That brings us to Giuseppe, Anu, and Abdullah. Do you folks need to share your screen?
Wait, if you don't mind, can you let LA Patel go first? I'm expecting a few more members
Sure.
to join the call, so that would probably give them time. And, well, worst case scenario, I can present it myself.
Yeah.
I'm here if you want to start.
Sorry, who's here?
Abdullah.
That was
Oh, Abdullah,
Abdullah.
you're here. Nice.
Yeah.
Okay, yeah, okay. I'll proceed then, if that's okay. Yeah,
Yes.
so let me take some time to share my screen. It's been some time since I've used
I
Zoom.
probably will have to make you a co-host so that you are able to share your screen, and I'm gonna stop sharing my screen. And now you should be able to share your screen.
And, okay, yeah, that should be right. Okay, can you see my screen?
Yes, we can see the in-place restarts proposal.
Okay, great. So Abdullah, feel free to correct me. But the point here is basically we'd like to present this new feature. Oh, and actually, by the way, this link here is listed in the meeting notes, right below my name. So if you want to click on the link yourselves, but anyway, continuing. So the point here is basically proposing this feature from JobSet. Of course, like I don't expect to go like through the whole design here. There's a bunch of stuff in the document. But I think it'll be a nice exposition for a larger audience. It's been already proposed in the JobSet repo itself. But anyway, provide some context. The name of the feature is In-Place Restarts. And the motivation is the following. Let's say you're training an LLM model using JobSet. You have a bunch of workers, let's say 1,000, each one of them running in their own node. And let's say a failure happens. Well, the way this type of model training works is that if any worker fails, you will have to restart all of them. And well, if you're talking about, let's say, 10K workers running in take 10 nodes, especially when using accelerators like GPU and TPU nodes, it can take a lot of time to restart everything, as in deleting all child jobs inside of JobSet, which implies deleting all pods and recreating all of them and scheduling all of them and make them running again. That can take some time. And the point of this feature is basically speeding up this recovery time, because when we are running at this scale, every minute of not training the model costs a lot, and we can expect to have multiple failures per day at this scale. And yeah, this is the motivation of this feature. And the way it works is, I'll preface by saying it's a bit hacky, especially for the first version. We expect to have upstream changes for the long-term solution, but until then, for the short-term solution, basically works as the follows. Let me perhaps show this image right here. I'm not sure if it's too small to present, but basically the way it works is, let's say we have two nodes, each node is running a worker. The idea is, if a worker fails, there's a sidecar running inside of the node that is polling the container runtime. And if it checks that the worker died, it tells an orchestrator to Valkey. Valkey is essentially a fork from Redis. And this orchestrator watches for Valkey, and if it notices that any worker dies, essentially sends a message to all agents telling, oh, hey, one of the workers died, therefore you must restart your worker. That's the high level view. Again, I'm not going to go through the whole design doc. I don't think there's time for it in this meeting, but feel free to give any questions. And yeah, Abdullah, do you have anything that you'd like to add? Like perhaps I'm missing something here.
No, we've got Anu as well on the call now, and Sergey.
Oh, nice.
I would just pause and see if anybody has any questions. Is the overall flow clear? What we're trying to do here?
Go ahead, Kevin.
Yeah, I guess I'm a little bit unclear on what the long-term solution for this actually is. I'm interested in like what are plans for effectively kind of phasing this away and letting it work in upstream, but I couldn't really find that proposal or anything linked here in the doc mentioning what our plans are.
So when you say a long-term solution, so at the end of the day, there are a couple of issues that we discussed, right? Like on the issue related to how we're going to detect failures on the like the sidecar, right? Having like right now, directly pulling container runtime to check for the like main containers failure status. And there was another issue. I forget what was the other issue. What was the other issue that we had?
I think with the CRI API.
Right, the container runtime, right?
Yep.
Yeah. Oh, I know you're here. Sorry, you can take over as well.
Yeah, I was wondering if Sergey wanted to take this, but I can answer. Yeah, so as Abdullah said, there's like a couple of KEPs that we plan to propose to address different issues that I think, Kevin, you brought up for the design. The first one I think is the most important. It's like we want to have some form of container level failure policies to ignore certain error codes on not like for non-failure. So that would allow us to restart the container, kill it and restart it via container policy instead of like the hacky sidecar approach we're proposing right now. Which essentially allows the container to live forever because kubelet restarts it on any error. So that would be the first one. And then the other one, which I think was brought up, was that we're using the CRI, like the container runtime interface, and how scalable that is and how safe that is. So right now we don't have a great solution to address that, but I think Sergey is planning to propose a different KEP. I'm not sure if it already is proposed in upstream, to have a way for one container to tell another to get restarted while ignoring the restart policy, and to build that into kubelet instead of how we're doing it now with CRI. And yeah, you can probably talk more about that if we're interested in that. So those are the two we're proposing to address the two issues that were kind of called out. However, I'm not sure like what version of Kubernetes those will be planned for, and when that will get done. So in the meantime, we do want to have this version that Giuseppe is presenting in parallel.
Yeah, just to add on that, yeah, we do plan to have some issues resolved, like make this solution better. Kevin, if you're asking about very long-term proposal, like is in place restart will be natural things that everybody doing all the time, or it will be like specific for Genk scheduling, like if you have a bunch of pods working together and you somehow can give them all signal, like do something all together, like a restart, for instance. I think Genk operating on pods is a very interesting thing. So sending all of them notification to do something, like to either stop or restart or um, doing something together would be very useful for many scenarios. And right now we do it with all the various hacks on the way, like all the various DUI, do it yourself on the way. Like Signal is not sent via Kubernetes channels; it's sent via Redis. Or like containers need to have this orchestrator that is not natural for native for Kubernetes. It's something that customers implement themselves. So all these pieces are now kind of do it yourself, and we will make do it yourself easy. And then later, I would expect that if the scenario will be very useful and many people will start using it the same way, then we can start doing like, oh, can we improve it and make an API on a bunch of pods to do some action? And that may be a future that you're talking about.
Yeah, I mean, that all sounds good. I was just, yeah, and then at least the design, it'd be great to kind of have these called out, just because it was a little unclear to me. Like this does feel like a short term or medium term solution, and I'm fine with that. But I'd like to at least make sure that there is also an interest in kind of phasing this away for a true solution in Kubernetes. And that's all I was just trying to say with the doc, is to maybe call that out and make it a little bit more clear what the plans are.
Yeah, I don't think we have a proposal, like specific proposal how it will look like when it will be like Genk, like bunch of pods API, like API for manipulating bunch of pods, like sending notification to bunch of pods. We don't have this proposal yet, but you may think about it. Maybe we need to at least try to express what it may look like without any specifics.
Yeah, and so I know there was also a couple others that were around, like max restart time, and there was another one. I think it was kind of allowing containers the on failure policy with the job controller. I don't know if those are also related to this or not, or will it be kind of like those are not solutions we'll pursue with this one? Because there's a lot of keps around
Yeah,
this, and I wasn't sure which
those are
ones.
those are related because to do it kind of do it yourself scenario with that we restart containers in place by emulating the crash, or like by forcing them to crash and restart. And you cannot do it if you have a job with restart policy never. So we need to work around it somehow. So you either need to find a way and have a cap that will say like this is a restart and it's not a crash. Like it's a restart action that is even for a job will not cause pod to go into failure state. Or we need to I think it's a longer term, like we have a bunch of caps that we propose, but longer term we may have this like this is a restart. This is not like this is a typical action. Don't treat it as a failure. But meanwhile, we want to have forcing container to crash and then treat it like to initiate the restart. And to do that, we want to have temporarily disable certain failures and say those failures are not causing the job to be marked as a failed, and those be rescheduled someplace else. So yeah, it's related to that.
And so for this design, Giuseppe, do we track the exit codes for these containers also? 'Cause that wasn't as clear in the previous design.
Yeah, for this current version, we don't actually track the exit code. So I guess like one follow-up question from you is that you can use the pod failure policy, right? Because of this. So yeah.
Yeah, I guess I'm just wondering, like, how will you detect like a hardware failure or something that will always fail? And then like, how do you know when to kind of stop this early versus just continuously restarting?
Mhm. Yeah, that's a good question. Like currently, how the design works is that like in a hardware failure, probably the pod will just die, not even the process itself, and that can be detected like differently from a worker failure, and it's currently handled the same way, but it can be made to be handled differently. Um, But again, we are not tracking that. Like we can also track the exit codes, by the way, but in the current design, we are not tracking them. Yeah.
Okay, thank you.
Do you have a question?
Yeah, I had to
Mm.
unmute. I was just finding the right button. I pasted in the chat. There was a comment from Daniel, and I'm not seeing him on the call, where he was basically approaching this particular topic from two different angles. One was to update the current validation such that we will allow, in case when you're setting pod failure policy, to use the on failure restart policy. The only comment that he has in that particular issue is that it's apparently more complicated than it sounds. And the other part is making the crash loop back of timing tunable. I remember that Tim Auclair and Laura Lawrence, if I remember correctly, her name, are working on this topic, because I remember I went through production readiness for that cap in the past two releases, more or less. I'm not seeing any additional comments with regards to those two approaches. Is there any follow-up why we're not pursuing either or both of those, rather than going all the way down to container runtime and skipping the kubelet communication with this, in, like you mentioned initially, in a very hacky way?
Mhm.
I
Sorry,
can,
go on.
yeah. So the first one that is mentioned there with the pod failure policy using on failure, yeah, that one is the ideal way to do it, I guess. Like our workaround to that is the sidecar. And it's sort of the same discussion we had with Kevin earlier in the call, where Sergey mentioned that there's a few ideas and KEPs that will be proposed to not use the sidecar approach. I think the exact change with restart policy being on failure and having a pod failure policy is kind of controversial, just because there's a lot of edge cases and race conditions we may run into with it that are explained, I think, in the linked comment. And so I'm not sure that Signode will agree to such a change, but I think Sergey has proposed some ideas around that or similar to that, like a container level failure policy that we may end up using. So yeah, I guess the first one is still under debate, and we're not sure we want to go down that exact route. The second one you mentioned with the kubelet back off, yeah, you're right that Laura and Tim have I think it was shipped in 132, so that already exists today. And I think it's alpha in 132. I'm not sure what the graduation looks like, but yeah, that one is sort of addressed, and the first one is still open question.
Does
Yeah,
anyone?
so I guess, sorry, go ahead.
Yeah, go ahead. I was
Oh,
just
I was
asking
gonna
if
say, yeah,
anyone
so
has any.
yeah, we don't have ideally we would have like both, and that would make the design a lot simpler than the sidecar workaround. But right now, we don't have the first one, and I think we're still trying to convince Signode that we want the first one, or we have some sort of workaround for the first one.
Okay. I believe. Yeah, go ahead, Abdullah.
I was just saying, like, those are going to address, like, particular problems that, or like hacks that the agent is implementing right now. But the overall, like, idea of how we broadcast a signal to restart a group of pods, I don't think we have anything in upstream to address this general problem. And so the more the more complex part of this proposal, which is having this Valkyrie side channel to communicate the or broadcast the restart, will probably continue to exist. And I wonder if anybody else, like in the community, has tried to address this problem in general as well. Like, how do we broadcast a restart signal? What they're doing. I've seen implementations before where it is, implemented in the workload itself in a very hacky way, right? For basically the training job itself, like in the training code itself, like at startup, it looks up all the siblings of our each pod, looks up all its siblings based on a specific pattern, and using headless service, they can find each other, and on startup they try to implement everything we've done here. But of course, like, this is like, I can't ask users or customers to inject this piece of code for you. So we're trying to find solution that is composable with the workload container.
Go ahead, Kevin.
I was just curious if will this also be something useful for leader worker set, or is the scale for leader worker set a bit smaller than this?
I would say the latter. It's small enough that I don't know if we care too much about like recreate versus restart, because you are restarting a specific replica, and the replica is probably like 4, 5, 10 pods. But for the training, it's much higher, much larger number of pods.
Okay, thank you. That makes sense.
We want to talk quickly about like how we're gonna introduce this to job set. Giuseppe, I don't know if you talked about this. So we discussed that we're gonna have a sidecar. The orchestrator is gonna run as a sidecar to job set. But we would like to introduce a couple of changes to job set to basically because we still need like the job set controller to play nice with this. I don't know, Giuseppe, you didn't mention that, but we want they introduce an annotation. For example, the orchestrator will communicate how many restarts were done. So we're going to set that as an annotation on the job set, and the job set controller will take that into account when deciding if the job set should move into a terminal state and fail the whole job set. So that's what the one thing that we will have to introduce into the job set controller itself.
Yeah, and I think I like the pattern you all are going with. I would hope that there will be a KEP to job set, like to formalize this a little bit more, and then we can discuss that one more there. But I think the idea of annotations and making it a little bit more clear that this is an alpha feature is good, and maybe not having the as an API change in job set quite yet. I like that plan.
Okay. I'm hearing no additional questions or comments on this particular topic. with that, we can then move over to Ally and his topic. Ally, do you want to share your screen?
Yes, please.
Hold on, let me find you. Yeah, you should be able to share your screen.
Okay. Can you guys see the slides?
Yes, we can see supporting the array and queue.
Okay, awesome. Yeah, so hi everyone, my name is Alay. I have been looking into this problem of supporting DRA in queue for last few weeks. And I wanted to present some of the core ideas in the design PR that we have opened today, and review it, open it for discussion. So today I'll be talking about some of the core ideas there. At the end, I have a POC demo. I'll go walk over that demo, and then we can open it up for discussion. So before we look at DRA in queue, I just want to level set on what the migration from device plugins to DRA world looks like really quickly. So on the left, you can see a pod with device plugins. It has this simple API where you have example.com at the very last line /GPU, which represents what the workload user wants here, which is they want two GPUs here, and the system is going to provision 2 GPUs for this pod. With DRA, this API gets a little bit more verbose, where at the bottom you see a pod which is referencing a resource claim. The resource claim here has a request of GPU, and the count is set to 2. Both of these resource claim template and pod are namespaced into the userland. And this particular resource claim template references a cluster scope object called device class. And this device class has, this device class basically is a blueprint of what this request is going to consist of. So in this case, we can see that user is requesting a device class gpu.example.com, and the device class has a cell expression which says I want a GPU with a specific driver, and that driver is gpu.example.com. Okay, so with that context, I want to dive into how this could be achieved in queue. In queue, what we want is you want to take this user workload on the right and set up some kind of a quota mechanism so that all the niceties of queue can be made use cases in case of DRA devices. So in this design, what we are proposing is a change in the resource flavor. Well, a change in the quota API, where we'll introduce a new field called kind. This kind field will be set as a device class. This is basically a differentiating factor between the existing core devices or devices from device plugins, where you have a specific field called kind, and that is set to device class. So queue will know that this is a DRA device quota. Then there is another field called device class names, and this is a list of all the device classes that the cluster administrator can set up quota for in this particular configuration. This will then have the nominal quota of 2. So the intent that the cluster admin is expressing here is that for any resource claim that is asking for a device class called gpu.example.com, I want to restrict the users with a quota of 2. So only 2 devices for those device class can be provisioned in workloads that are requesting resources from this cluster queue. Okay, yeah, so that is the API change. Internally, what Q will do is Q will, the POC implementation I have is that Q will note this particular canonical name that user has specified and reflect in the status of this cluster queue the usage and reservations for this device class. So whenever a workload comes in, Q will track all the way from the pod references back to its device class, figure out the requests, number of requests that user is making, and reserve it in the status. So with that context, I want to dive into the demo next. For the demo, I'll have to change my sharing mode. Give me 1 second, sorry. If Maciej is here,
Yeah, I'm
Maciej, can
here.
you take the screen away from me? Somehow oh, actually, never mind, I found it here. Okay.
You are sharing a video, by the way.
Yes, I am. Give me 1 second. Okay. Okay, is my screen visible?
Yes, we can see a video.
Okay. So in this demo, I have the example DRA driver setup. I'm going to show the setup before. And then I'm going to walk through two scenarios. The first case where a cluster admin wants to set up quota for entire set of GPUs exposed by the example DRA driver. And then later on, the cluster admin wants to set up a quota for sharing for GPUs that are used in sharing mode. So time slicing and space slicing later on in the demo. So let's get started. So first, you can see on the left that we have a kind cluster with two nodes, and we have the DRA example driver installed. This driver comes with a default device class, which is the gpu.example.com. With that, let's set up a watch for the jobs and resource claims in a namespace. Now, on the right, I'm going to walk through the cluster quota setup. As we looked into these slides, a queue called single GPU cluster queue is set up with single GPUs as the canonical name and a device class with nominal quota of 2. And then this is referenced by a local queue, and we are creating a resource claim template here in the user namespace referencing the device class. So with that, let's create those resources. Okay, so you can see that the local queue in GPU test 1 namespace is created on the left. On the right, I'm walking through example job workload. In this, you can see that the resource claim section has reference to the resource claim template that was just created. So basically, the user is requesting a GPU, and that template has a count of 2 GPUs. So 2 whole GPUs from this example driver will be provisioned for this job resource. Okay, so going ahead and creating those that job object. You can see on the left that job was created and 2 resource claims were created for it. And the local queue shows that this workload was admitted. Now that we know that the nominal quota was 2, we can create another job requesting GPUs that we expect to go in pending state. But before creating that, let's look at the cluster queue status. This status reflects the flavor usages, which is 2, and the reservations for the job that was already created. Creating a pending workload now, you can see that the system has put it in suspended mode. We do not have enough quota for this job. Now I'll be showing the shared GPU example. So in this case, the cluster setup is a cluster queue with shared GPUs. And there are 2 device classes, TS shared and SP shared, both of them representing different modes of sharing. Because these device classes are not created by default by the example DRA driver, as an admin, we're going to go ahead and create those device classes. You'll notice that in the TS shared device class, there is a time slicing configuration. And then in the SP shared device class, there is a space partitioning configuration. This will be read by the example DRA driver, and the GPU will be provisioned accordingly. So I want to explicitly call out that this design supports multiple device classes being allocated to the same quota. Okay, so on the left, you can see that we've created a new local queue that points to the shared cluster queue. And we'll look at the job resource that will request GPUs in shared mode. So we have a time slice job and a space slice job at the bottom. Both of them have 2 containers which are sharing the GPU that will be provisioned from the resource claim mentioned in the job spec. Going ahead and creating those workloads. You can see on the left that 2 new jobs have appeared, and resource claims for those have appeared as well. And in the admitted workload section, you can see 2 devices. Checking for the cluster queue status, again, we can see that the usage is reflected there, which has fully saturated the quota. Creating the pending workload now would send it to suspended state. Okay, that's all I have for the demo. I want to open it up for questions now and any further discussions.
Go ahead, Oliver. You were first.
Sorry, trying to mute. This looks great, but went a bit fast, so I'm trying to understand. So this works on claim templates, resource claim templates being requested by pods, or this works also on resource claims?
the design supports both resource claims as well as resource claim templates. In the POC,
Okay.
I just have
Okay.
the resource claim templates, because when we go through the implementation, we'll have to make sure that if a resource claim is provisioned for a pod and it is shared by another pod, then it doesn't get double counted against
Yes.
the quota. So that is something that I'll have to add to the design and be sure in the implementation. But there is no reason why we couldn't support that case.
So okay. So just to paraphrase, so first of all, this works on pods, obviously not on claims, right? So I can create as many claims as I want. These are not going to be queue managed in any way, right? Okay.
Yes.
And second, you're saying you indeed have the goal that because here you demonstrated the shared device more than the shared claim, right? So you have the goal to support shared claims, where if I have 3 pods that share the same claim, then this will be single counted. Okay.
Yes.
So it's not just keeping track of the size of the claim, but also the ID of the claim. Essentially. Right, you need to know the claim name, right, to do that. Not just you need to keep track of claim names.
Yes, we will
Right,
have
so
to do that.
in other words, and I'll stop there to let other people talk, but that means when we do the accounting of resource usage, it's not just the device class, or in the classical sense CPU and memory, or nvidia.com/GPU with the count of such resources that are already being consumed, but it's how, right? It's a map from resource claim identities or names, or namespaces and so on, to the actual count.
Yes, that is
Okay.
correct. So in the POC, I had to create a map from the resource claim or the device class back to the canonical name that is defined in the cluster queue to account for how many devices are requested for this particular device class, right? So that map is there. I have to modify that structure to also account for a resource claim that could be shared. So, I think you've paraphrased it accurately, and yes to all the questions you have asked.
And so this whole design works because claim allocation is actually lazy, right? The creation of the claim doesn't mean that the resource is reserved at the claim creation, but it's only at the time the claim is being used. Is that correct?
Well, that is not, well, that is one way of looking at it. The way I am thinking about it is this particular design looks at workload and not resource claim. Queue has to have a workload in order for it to account for the resources that are used. So in other words, let's say if you have a resource claim that was created, and through some other scheduler, which can provision request for it through node prepare and unprepare without pods, then those all kinds of things would be out of scope. You should look at the workload that is being requested, map the device class from it, and then account for those resources. So that's how I'm approaching it.
That perfectly makes sense from a the role of queue and the scoping perspective, but my goal is holistic, right? I want to prevent the user from using more resources than what they're entitled to, and so if resource claims are eagerly reserved, then I would have to preclude users from creating resource claims directly. Right. Otherwise, they can still, they can use queue to manage their quota for their workloads, but they can still abuse the system and do a denial of, resource attack on the system, essentially.
Yeah, I think when this eager allocation of resource claim is supported in Kubernetes, I don't know if there are concrete plans, but when that happens, we'll have to incorporate that in queue somehow to account for those things. But as of now, it would be out of scope of this design. That
Okay,
makes sense.
understood. Thanks.
By
March,
eager
you're up
allocation, do
next.
you mean? Oops, sorry.
Sorry, Kevin, can you put your hand?
Yeah,
Martin
sure.
was
I
already
just,
in line.
yep, got it. Sure.
Kevin, if you have answer to what was discussed right now, maybe you should go first. I have a slightly maybe different topic so that we don't change context back and forth.
Sure. Yeah. My question was just about what Ale had just said with when you say eager allocation, does that refer to what we used to call immediate allocation?
Yes, yes.
Is that what? Okay, got it. Yeah. There's no plans to support that
Yeah,
in the
in that
structured
context, that
parameters
makes
model.
sense. Yeah.
Yeah. So that's not something you'll need to worry about going forward.
Yes, I mean it's more like when there's a shared claim again, and we have the shared claim is used and released and used again and so on, right? That maybe, but let's take this offline. I think I got the answer.
Okay, couple comments. Thank you very much for doing it. That's definitely like a great step in the right direction. I haven't done the PR review. I've got a couple questions here to better understand it. And if we have time, maybe we can get the answer right now. So first of all, why do we need multiple device classes for the resource? So there you have like a list. Why is a list not a single one? And maybe connected questions. We duplicate this basically like a type definition in every cluster queue that is in the cohort, and maybe they are sharing this definition may be slightly different in each of them, like different elements on the list and so on. Have you thought about actually making it a part of resource flavor instead of cluster queue? So that would be like the first question of me.
Okay, yeah. So let's get. I can answer the first one first. So the reason. So just to set context, the previous attempt of this design by Kevin Hennon was just using a single device class. So that's where we started this exploration from. But then while I was going through all the use cases that are set up in the example DRA driver, where there are different ways of sharing resources, namely time slicing, space slicing, and make partition. Those are the three popular ones. I quickly learned that if we just have a single device class in the quota, and if so in the demo, I showed that there are two quotas, one for single GPUs and other for shared GPUs, right? In case where we have a single device class entry, the shared GPUs is hard to account for because both the space partition and the time partition sharing will look at the actual allocation of one GPU, right? And in that case, if you have separate quotas set up, what device class do you count this particular request against? That was the challenge that I ran into. So in order to solve that problem, we have a list of device classes where if the actual allocation or the request happens to any of the given device class, then the cluster queue administrator can configure that and have the system set up. So long story short, it will open up use cases for cluster administrators to mix and match their quotas across different device classes.
Okay, and what about the second part? Why to put this whole definition in cluster queue? not in resource flavor or somewhere around it, and then just point it in the cluster queue definition, so that multiple cluster queues that are defining quotas against the same flavor are guaranteed to have this very same definition of the name, like the same device classes and so on. So
Yeah,
that the quota and borrowing and all of that things work a little bit cleaner, and it's guaranteed that when you say two, that everyone means the two of the very, very same resource type.
Yeah, that's a good question. I had not thought about putting it in the resource flavor object. Although my question to you would be, why are the CPU and memory the core resources also present in resource flavor objects?
No, they are not. They are kind of core resources. However, the meaning of CPU and memory is very much connected to the resource flavor. Like, for example, you have a resource flavor defined against, I don't know, Intel machines, and then when you specify CPU, you kind of know that it's for CPU for these Intel machines that are in this resource flavor, and the same could be applied for the single GPUs that are very specific also to this type of machines for which you already defined CPU and memory. And it might be a little bit cleaner if we just have a name there and the definition slightly elsewhere. So, okay, if you need two classes, then okay, but let's make sure that everyone who is using this resource flavor and is using this name, and then we use this name for borrowing, lending, and so on, has to have the very, very same list of devices. And this doesn't get out of sync or defined differently on different cluster queues in the same cohort.
Got it. Yeah, I think that's an interesting idea. I'll take that as an action item to explore that API change and see if it works.
Oliver, do you have more questions, or can I add another one?
Go ahead first.
Okay, so we use workload for accounting, and workload objects are kind of protected from users from modification. So that's piggyback a little bit of Oliver's security concerns earlier. Yet, in workloads object, which we use for accounting, we will be referencing user-owned object resource claim, which can go away, can be modified back and forth, and so on. So, from the security perspective, the ownership, it would be great if all of the things and numbers that we use for accounting were owned or controlled by Q, so that nothing is changed behind Q back. Have you considered actually inlining claims and needs in the workload object, so that we are sure that we have like the complete pictures? Once we admit it, we have all of the numbers and they are fixed.
I'm sorry, can you define what you mean by inlining? So right now, when a user creates a job for resource claim, it will automatically trigger a workload creation that will have the exact resource claim that was defined by the user. So we'll have a reference to that resource claim. Do you mean that along with the reference of the resource claim, we want to put in the definition of the resource claim itself so it doesn't get modified?
Yes, that's my question. So I'm not definitely like a DRA expert. I'm wondering what are the consequences of leaving that for the user, and possibility of getting out of sync of what the quotas are and what is in the claims and so on.
Got it.
So
So I think
we do have all of the pod requests in workload, and they are protected with with access to the workload object. So the regular user cannot modify it once it is in, and we are sure that, well, quotas are there. Here we have half of the definition in workload and half of the definition in external object that is owned by the user, which is subject of going away or whatever.
Yeah. So I think Karen can keep me honest, but so far, what I know is that the life cycle of a resource claim is tied to life cycle of a pod. So if a pod exists, then the resource claim will exist in that namespace.
What do you mean by exist? So a user creates a claim, a pod references it. When the scheduler goes to schedule that pod, at that point, it will allocate some GPU, in this case, to that claim. It'll get bound to that claim. That's stored in the resource claim status. That pod goes off and runs. That GPU gets added through the DRA driver running on the node where the pod had landed. It runs to completion. Pod then dies. GPU gets deallocated, and it then gets unbound from the claim, so that device is now free to be used by some other pod later on.
So I think the concern here is that once the allocation has been made for a GPU to the pod, what if user comes in and deletes the resource claim?
If the resource claim itself is gone,
or modified.
that's totally
So-
possible.
Yeah, right. Or,
You
or
can-
edit to use less of a resource. Otherwise, adjust it in a way that would change the accounting.
So it's immutable in that sense. You can't adjust it. But you can delete it. And that's a completely valid thing to do. You can delete the claim because the driver on the node side has to have checkpointed what it is allocated so that it can deallocate that later.
So my concern here is that we don't do admission, scheduling, and starting atomically. So we look at, let's say, job definition. We calculate the needed resources. We check it against quota, and we let it in. Okay. Couple seconds later, job set controller realizes that the workload has been unsuspended and starts creating pods. And within this brief moment, there is a possibility that resource claim is modified. So we already admitted the workload. We check the balances, and now let's say GPU count from 2 or whatever from the specific type goes to 200 or something more fancy or whatever, either via object modification or via object creation and deletion and recreation. And then job set controller creates pods. Pods get much more generous claim, and everything is fine, except Q wouldn't let the modified resource in. However, it's already kind of too late.
When does Q enforce its quota? Is it at
It
the time
doesn't
the pod is
enforce
scheduled, or?
quota at this moment. So we could, once we realize that something was modified, we could suspend the workload and unsuspend it. However, it would be good to have it clearly written in the cap. What is the behavior if something gets modified? Plus, we need to realize that something was modified, and we don't know because we don't store any such information in the workload. If we don't
So I guess
notice,
sorry, I was just asking in general, when does you enforce quota, not in this case? Because once the resource claim, once the device has been bound to the resource claim, the actual allocation gets stored in the resource claim status, and that is immutable. You can't change that for the lifetime of that pod, that resource claim being referenced. You can change the spec to say, oh, now I want 500 devices, but that's not going to be, it's not going to trigger anything, at least in the standard DRA way of doing things. It doesn't trigger these 500 devices to suddenly be allocated to the pods. Whatever the status has in it is what is locked in place for the lifetime of that claim being referenced.
Okay, so we do not expect currently in queue that the resource consumption of an already admitted workload will go up. So we expect that the definition may change, and then we notice that there is a difference between what is in the workload and what is in job definition. For example, someone modified pod count, and we can act accordingly because we can spot the difference because the number is in the workload and is in the job definition. These two numbers don't match. It means that the workload was modified. We suspend and admit the workload again. We notice it, and then maybe like the readmission fails because there is too little resources. However, without the actual DRA consumption in the workload, we have no way of knowing whether what we admitted was is still what's in the system, because there is only a single number.
So
there are no.
But that's where I'm confused. Why not? Because when the workload starts, the amount of resource that's been given gets locked in place in that resource claim status. That will not change for the lifetime of that running pod, and it'll only ever have access to
are
that.
not running yet. The pods are not running, so
okay.
The job before we admit it has not created any pods. So resource claim is not locked, so it could change. That's not like a super big security threat. However, it would be good if we could have it addressed explicitly. Either that's known problem, or maybe put the number in the workload so that we can catch discrepancies, or put some other mechanism in place.
Yeah, I think what you're alluding to is a race condition where if between the workload getting admitted and actual allocation happening, if something comes in between, not necessarily notorious in nature, but if something changes, then queue should be accounting those resources. And I think it is fair to put this particular resource claim in the workload object so that it is explicitly clear to everyone involved, all the actors involved in the system, that this is the schema that queue admitted, and this is what it expects workloads to run from.
Yeah. That's what I was asking for.
Okay.
Yeah.
In the interest of time, because we're already 5 minutes past and people are slowly starting to drop. I see that Oliver left the comment to Ala in the chat, so the two of you can follow up on Slack and other mediums. Thank you very much, everyone, today for the lively discussion, and see you in 2 weeks. Bye, folks.
Thanks, folks.
All right.
Thanks.